Good evening, everyone, and welcome back to AISC's Night School. This is Bracing Connections and Related Topics, presented by William A. Thornton. Today is September 29th, 2014, and this is Session 2, the Uniform Force Method. My name is Brent Liu. I am with AISC, and I will be moderating this evening's presentation. I want to welcome back our presenter, William A. Thornton, PE and PhD. Dr. Thornton is a corporate consultant at Surveys Corporation of Roswell, Georgia. He is the winner of the AISC 1995 T.R. Higgins Lectureship Award, as well as the 2003 AISC Lifetime Achievement Award. He has served as an invited lecturer numerous times for AISC and various state structural engineering associations, primarily focused on connection design. He is the author or co-author of many published papers on connection design. He is a member of ASCE, AWS, and RCSC, and he currently serves on technical committees for AISC, ASCE, AWS, RCSC, and served as the chairperson of the AISC Committee on Manuals for more than 20 years. It should also be noted that in 2013, Dr. Thornton was inducted into the National Academy of Engineering. I want to welcome you back, Bill. Thanks for being here, and I'll hand things over to you.
Okay. Thank you, Brent, and good evening or good afternoon, depending on where you are. This is the second session in this 8-session webinar on bracing connections and related topics. This slide shows you the topics that we'll be covering in each of these 8 sessions. Last week we did a lot of basic principles. We did the lower bound theorem, corollary to it, that sort of thing. Today we will concentrate on the development of the uniform force method. And in subsequent presentations we'll look at bracing connections and details. That's next week, or 2 weeks actually from tonight. Then we'll look at some corner connections, some non-seismic and seismic. Those will be 4 and 5, and then chevron gussets for 6 and 7, non-seismic and seismic, and then we'll finish up with some additional topics. Some of them are probably still up in the air, but maybe development of fills and gussets coming down to base plates and that sort of thing. Tonight's session will cover all of the items that you see here. The uniform force method and all of its the things that are associated with it. The geometry, control points, admissible force field. We defined that last week, but we'll talk about it again. We'll do the beginning of a small example, which also will be done in session 4. We'll look at the special cases 1, 2, and 3. Special case 4, which is a new one. The research basis for the uniform force method, depending on how much time we have, we'll get into an orthogonal development for the uniform force method and then do a couple more examples and a summary. The uniform force method, what is it? It's a geometric method to determine the statically indeterminate force distribution in a vertical bracing connection. The method evolved from research sponsored by AISC, performed by Ralph Richard at the University of Arizona back in, the mid-'80s. This gives you kind of the geometry that we're talking about and the admissible force field. The admissible force field is one that's in equilibrium with the applied load. And really, I think the beauty or the basis for the uniform force method is that all the forces that act on the gusset, as you see in this picture, the brace force, the gusset to beam force, the gusset to column force, all of these forces are forced to intersect at a single point. So that we end up with a coincident or a concurrent system of forces, and we know that we can satisfy equilibrium for this gusset without any couples. This just shows you basically the forces that are involved in it. We will be developing these as we go along. This sort of lead-in slide here, the quantity in the box is a constraint that the alpha and the beta quantities need to satisfy. Alpha and beta are the locations of the connection centroids. And what about an admissible force field. An admissible force field is an internal force distribution in equilibrium with the applied forces. That's basically all it is. We need to do free body diagrams. We need to have free body diagrams for all parts of our connection, just as we have to have them for all parts of our structure. The load path that actually develops is intimately associated with the admissible force field that you choose. And last week we saw admissible force fields that were generated by three methods that exist out in the industry today: the parallel force method, the KISS method, and the uniform force method. And today, and for the rest of this webinar, we will be talking about only one of those three, the uniform force method. The control point geometry, and we'll be talking about control points shortly, is dictated by the constraint. Alpha minus beta tangent theta equals E sub B tangent theta minus E sub C. Alpha and beta locate the gusset connection centroids. Sometimes you'll see in some of these slides another set of quantities, alpha bar and beta bar. When designing a connection, alpha and beta can always be chosen to satisfy the geometric constraint. When checking a connection designed by some other method, the connection centroids may not satisfy the geometric constraint, and this is where alpha bar and beta bar appear. These would be the actual connection centroids, and will not necessarily satisfy the constraint. And if that happens, instead of having a nice concurrent or coincident set of forces on your gusset, you'll have some couples. So all of the forces do not act at a single point unless you satisfy the constraint. This shows you in more detail what we're talking about here, and all the quantities that are defined on this drawing. Alpha is the distance from the face of the column flange to the centroid of the gusset to column connection. Beta is the distance from the top flange of the beam, in this case, to the centroid of the gusset to column connection. E sub B is the half depth of the beam, basically gets us to from the working surface here to the gravity axis of the beam. E sub C, likewise, is the distance from the centroid of the column to the working surface on the gusset to column connection. There are three straight lines that are shown here that we'll go into detail about, and they involve some what I'm calling control points. Control point A is the beam control point. It is at the gravity axis of the beam at the face of the column, and control point B is at the gravity axis of the column at the face of the beam. Now, it could be the top flange of the beam, it could be the bottom flange of the beam, it just depends on where the gusset is. The angle theta given here is the angle measured from the vertical, not the horizontal. It could have been measured from the horizontal, and honestly, I don't remember why I took it from the vertical. It would have seemed more logical to me to, since we're talking about a first quadrant situation here, to measure it from the x-axis, but the method has been around for 25 years or so with that alpha, and it's probably a little bit late to change it. You see a coordinate system here with its origin at the work point. The x coordinate goes to the right, and the y coordinate goes up. This is the same thing well, if you look at the beam, if you go back one, we don't see the beam in this picture, but the beam is right in here. If we look now at a free body diagram of the beam, that piece of the beam is in equilibrium under these forces with absolutely no couples. You have only uniform forces on every edge, on the gusset beam to column connection, which is right here, and at the gusset to beam connection, which is right in here. Likewise, for a piece of the column, the same thing. All of the forces on these three free body diagrams, the gusset, the beam, and the column, are all in equilibrium under the forces that you see here without any other forces outside of the region of the connection. These slides show the control points. Control point A is the beam control point. Control point B is the column control point. These are really fundamental to the development of the uniform force method. Coming back to this slide, we've got some more information added on at this time. You see that I have equation numbers given. We have equation 1, which is the equation of the straight line of the brace direction. And equation 2 is the equation of the straight line of the force that acts at the centroid of the gusset to beam connection passing through the control point to the common point, gusset control point Q over here. And likewise, over here, we've got an equation 3, which is a straight line that passes from point Q to B to the centroid of the gusset to column connection. These are the equations of those three straight lines. For equation 1, y equals 1 over the tangent of theta times x. For the equation for the beam force line of action, it's y equals E sub b over alpha, which is its slope, times x, minus the y-intercept, which is E sub b over alpha, times E sub c. And the equation for the gusset to column force line of action, y equals beta over E sub c, which is a slope, times x, times the y-intercept, plus the y-intercept, which is E sub b. These are the three equations. These equations were first developed in about 1985 when I was trying to come up with a kind of an analytical way to represent the work that Ralph Richard was doing kind of empirically. If I take those three equations, 1, 2, and 3, and solve them, say to find point Q, take equation 1 and equation 2 and set them equal, and solve them for x sub q. That gives me equation 4. Take equation 1 and set it equal to equation 3, and solve for x sub q. That gives me equation 5. Now I've got two equations for x sub q. And x sub q given by these two equations must be equal. So, setting equation 4 equal to equation 5, we get what you see on this slide. And then simplifying that, all of a sudden you'll see a very familiar equation if you've ever used the uniform force method. The constraint kind of comes out of the hat here. Alpha minus beta tangent theta equals E sub b tangent theta minus E sub c. To satisfy the geometry of the uniform force method, the equality given by this equation, equation 6, must be satisfied. I think that this is the first time that I've actually formally presented this derivation, but it was first done a long time ago in 1985 at the Ionosphere Club of Eastern Airlines, which has been out of business for a few years after this. My flight was delayed. I just couldn't stand not working on this problem. And finally, I got something that worked that I could sort of hang my hat on. I know I've never presented this before because I've always felt that it's pretty transparent. You should be able to do this yourself. When this was first published, I think in the second edition LRFD, or before that, in my paper in 1991, I got a call from a New York engineer that said, well, this is just geometry, isn't it? It's no big deal. Yeah, it's just geometry, but I think it is a big deal because up until this point, there were all kinds of crazy ways to do this. I don't think that the parallel force and the KISS method are really crazy ways to do it. Those are the better ways. But everybody out there had some way that they thought they should do this, and most of them were really pretty bogus. So once you get this constraint equation, equation 6 here, you can take that, and it's really pretty simple to then derive all the forces, the formulas for all the forces that act at the gusset edges, H sub b, H sub c, and I always write them this way so that I can add them up and check that H sub b and H sub c has got to equal H, the horizontal component of the brace, and V sub B and V sub C, they've got to add up to be equal to the vertical component of the brace. And the P over R here is common to every one of them, so I usually write them like P over R times alpha, E sub C, E sub B, and beta. But you don't have to do it that way. I mean, if you were more of a purist, probably you should write them as P times alpha over R, because alpha over R is an indeterminate, is a dimensionless quantity. And the R here is just a parameter that I forgot to mention on an earlier slide, but it's the distance. We'll go back a couple of slides and show you what R is. It's just a geometric parameter. It's the distance from the work point to the point where a vertical raised from the centroid of the gusset at alpha meets the horizontal projected from the centroid of the gusset column connection. And where they meet, the distance from that point to the working point is r. It's just the geometric part of the uniform force method, and it really makes the final equations, just using it, pretty simple. The equations that you see on this slide here. So continuing, let's look at an example. This is a simple beam to column connection connecting to a column flange. We have a 16 by 57 beam, and we have a 12 by 65 column, and we have a WT 6 by 22.5 brace. We have a force in this brace of plus or minus 75 kips. All of the parameters that are defined that we'll calculate, E sub B, E sub C, alpha, alpha bar, beta, are shown on this picture. This is some of the data. We're doing this to the 14th edition, and it's an ASD example. The beam to column and gusset to column connections have 4 rows of bolts. That's what the n, little n equals 4 means. The length of the weld was taken as 20 inches with a 1/4 inch minimum fillet. In this case, we're using 3/4 inch diameter A325N bolts in standard holes, unless noted otherwise. And for double angles, we're using horizontal short slots. Short slots transverse to the direction of the load. They're actually horizontal in the legs that connect to the column. And the edge distance in the vertical direction is 1.25 inches. Minimum and the bolt spacing is 3 inches. The brace force, 75 kips, plus or minus. The slope is 43.6, and the theta angle measured from the vertical is 90 minus 43.6, or 46.4 degrees. So continuing with the parameters, you'd calculate tangent theta, which is the tangent of the angle, 46.4 degrees. E sub B is the half depth of the beam, 8.2. E sub C is the half depth of the column, 6.05. E sub C is equal to 0 for connections into column webs generally, except for this new case 4 that you'll see later on today. Calculating from the geometric layout, the height of the gusset is about 16 7/8 inches. That's this distance here, and we in this particular example, this clip angle here was centered on that, which gives me a beta, more or less centered, gives me a beta bar, which is going to be equal to beta of 8.5 inches. That's 8.5 inches from the bottom flange of the beam to the centroid of the gusset to column connection. Alpha, then, we can calculate alpha from the constraint. Alpha equals E sub B tangent theta plus beta tangent theta minus E sub C. So it's 8.2 times 1.05, that's the tangent of theta, minus 6.05, which is E sub C, plus beta, which is 8.5 times tangent theta. 1.05 gives me 11.5. Now you might say, well, why didn't we make alpha and alpha bar equal? We could have, but the reason it's not done here is just to show you how it works. Alpha bar, in this particular case, is half the length of the weld plus the setback. The length of the weld was given as 20 inches over 2, gives me 10, plus a half gives me 10.5. Now alpha itself was 11.5. So all I really need to do is say, I don't want to use 20 inches for the weld here. How about if I use 22? If I use 22 inches, 22 over 2 is 11, plus 0.5 gives me exactly what alpha is, 11.5. It wasn't done in this case just to show you that you don't need to do it that way. But if you don't have alpha equal to alpha bar, when you calculate this parameter r, you must use the alpha and the beta, not any of the bar quantities. It turns out that alpha bar is equal to, beta bar is equal to beta in this case, but alpha is not equal to alpha bar. So to calculate the forces, you must use alpha and beta that satisfy the constraint, which is written right here. If you don't do that, you won't satisfy equilibrium. So calculating R, you get 22.4 inches, and then continuing on, we're not using special load case 2 here, but this is anticipating the discussion a little bit later in this webinar. If you used special case 2, we would transfer some of the vertical brace component V sub B to the column V sub C. In this particular problem, we will take V sub B equal to 0, so I'm not going to discuss it anymore here. V sub C is equal to P. This sub A just means for ASD times beta over R. This is 0. And M sub B, because alpha and alpha bar are not equal to each other, we're going to have a small moment on the horizontal edge of the gusset. This term is 0. Delta V sub B is 0 in this case. We will discuss special case 2 in a little while. So continuing on, I calculate V sub B, which is the force, the ASD force, 75 kips multiplied by E sub B, which is 8.2, divided by R, which is 24.2, gives me 25.4 kips. H sub B is 75 over 11.5 divided by 22.4 gives me 35.6. And the remaining 2, really, of V sub C, let's do that one first. P times beta over R gives me 26.3. And H sub C, P times E sub C over R gives me 18.8. Now, because alpha and alpha bar are not the same, I've got 11.5 minus 10.5 times V sub B, which is 25.4, gives me 25.4 kip-inch couple on the horizontal edge. We could, as I said, have made the alpha and the alpha bar equal just by making the weld about 2 inches longer. Which is the more economic way to do it? I don't know. Check it out and see. But what you should do as a homework problem here, you should take V sub C and V sub B on the previous slide, and you should add them together and show that you get the vertical component of 75 kips, which is 75 times the cosine of the angle theta. And you should take the others, H sub B and V sub and H sub C on the next slide, add those two together, and you should get the horizontal component of the brace, which is 75 kips times the sine of theta. Just as a check, I mean, it's very common to make errors in this stuff. You got a lot of numbers to take care of, and I tried to make a point here, and one of the reasons why we're doing it this way is that when you calculate R, you must use alpha. When you calculate the quantity R here, this has got to be alpha. Do not make the mistake of substituting alpha bar in there when alpha bar is not equal to alpha. If you do that, when you come to do what I just gave you as a homework problem to check the V sub B's and the addition of the V sub B's and the V sub C's and the H sub C's and the H sub B's, you won't get the tangent. The cosine of 75 for the vertical and the sine of 75 for the horizontal. So you'll know right away that you've screwed up someplace. So we've done all that. M sub C would be a couple on the horizontal edge. The vertical edge between the gusset and the column. But in this particular case, beta equals beta bar, so it will be 0. You could have couples on both edges. And if you have a situation where you have the gusset welded to both the beam and the column, how do you make the decision as to which one to pick? Which one should be beta? Should beta equal beta bar, or should alpha equal alpha bar? And really, there's no answer to that question. Usually, we pick the beta equal beta bar for the bolted connection because it's difficult to carry any couples or moments on bolted connections, especially with double clips like this, because you've got prying action and all that to deal with. Whereas the weld is really pretty benign relative to any couple on it, provided it isn't too big. So usually, and I think it's pretty much universal, that whenever you have a welded, bolted situation, you always pick the centroid of the bolted connection and set that equal to beta. That's therefore beta equals beta bar. And let alpha turn out to be what it needs to be to come up with reasonable geometry for your gusset.
Okay, Bill?
Yes.
Yes, before we move on, we do have a couple of questions regarding the example.
Okay.
First First, as several of you pointed out, there are some corrections that were made to the example. I do apologize that we got the handouts out before that was caught, but we will have the updated version posted first thing tomorrow morning. So we, again, apologize for that inconvenience, but we wanted to get it updated, and we'll make sure you get those handouts in your hand tomorrow morning. Regarding a couple questions, Bill, for projects that are still being designed using the 13th edition, the question is there anything different in the process of using the uniform force method that's different that's now in the 14th edition manual?
Okay, do I need to repeat the question, Brent, or just
No.
has everybody heard the question?
Everyone's heard the question, Bill.
There is no difference between the 13th and 14th. It's exactly the same. If you read Part 13 in the 13th edition manual and look at Part 13 relative to this part of it anyway, the uniform force method, you'll find that it's exactly the same.
Okay. And then I have a couple questions. I'm going to go back to slide 28.
Okay.
I've got it, Bill. I've got it there.
All right.
There we go. Okay, a couple questions about combining welds and bolted connections. And the question is, does there need to be any adjustment made due to the fact that the gusset plate is welded to the flange of the beam, but we're bolted to the column?
I don't think so. I mean, the connection that's probably critical in that regard is that is the gusset to column connection and the beam to column connection. If one of those is bolted, the other one should be bolted too most of the time. There's no specific requirement for that in the specifications. I mean, you could argue that there is, but I don't think it really covers it exactly. But in the seismic spec, there's an absolute requirement for certain kinds of bracing connections that you use bolted or welded. But the other one, the gusset to beam, I don't see why that has anything to do with it. I mean, we've got the way this is connected. There's no reason why the deformation, the strain that takes place in the gusset to column connection, and that takes place in the beam to column connection can't be essentially the same.
Okay. All right. Next question is, does the eccentricity need to be transferred to the beam, or do you just account for it in the design of the weld?
Does the eccentricity need to be transferred? There is, if you look at the free body diagram of the beam, even if there's a couple between the gusset and the column, there is nothing in the beam outside of the connection. There's a local effect of the couple between the gusset and the beam in this case, which would have to be considered. But it's a kind of a local effect. I mean, we would look at, and you'll see this in some of the examples that we do later on, we would look at web yielding. That's web due to a vertical component. Normally what I do is I convert the couple into an equivalent vertical force, and I check the web of the beam locally right at just inside the flange, just above the flange on slide 28 for web yielding and for web crippling. But when I get outside of the connection, say to the left or to the right of the gusset in this case, there's no couple in the beam. It's just the local effect that's taken care of in the connection between the gusset and the beam, and it doesn't actually transform beyond the connection itself.
Okay. And then one more question here before we move on. The question is, if the gusset is welded to the beam and to the column, would alpha bar be equal to alpha and beta bar be equal to beta?
Not necessarily. There's a routine in the part 13 of the manual that gives you a way to come up with a kind of optimal distribution of the alpha and beta. so that alpha would not be equal to alpha bar and beta would not be equal to beta bar in general. But I would say that in a situation where you had welded, usually one edge of the gusset is going to be a lot shorter than the other. I would say the shorter one is the one that's going to be more critical for couple. And I would say that I would take the shorter of the two welds to be the one where beta, say it's the vertical part here, where beta equals beta bar, and let alpha and alpha bar be whatever they are on the longer edge. But if you want to split it up in some optimal way, go to part 13 of the manual. There's a little routine in there that introduces an objective function, and it introduces something called a Lagrangian multiplier to introduce the constraint. The constraint is the alpha minus beta tangent theta, etc., so that we satisfy that and we kind of minimize the objective function. We distribute the eccentricities in such a way that we minimize, say, the square root of the sum of the squares of the moments that exist on these edges. It's only one way to do it. I mean, I've never actually used that in any problem. Usually you can come up with a much more, say, down and dirty way of doing it instead of getting into any kind of fancy mathematical stuff like that. Just the shorter edge should be the one that has no couple. The longer edge is the one that's more benign relative to couple, so that's the one I would put the couple on. In other words, if it's the horizontal edge, then I would have alpha and alpha bar not equal to each other. If it was the other way around, I mean, suppose you had a very steep brace here in slide 26, the horizontal edge could be the short one and the vertical edge could be the long. In that case, I would take alpha equals alpha bar on the horizontal edge and let beta and beta bar turn out to be whatever they need to be to satisfy the constraint.
Okay.
You've asked me to mention, Brent, and I forgot that when you see red on these slides, there's some things that were changed at the last minute, like the title of this slide, 28, the whole thing is in red. We basically changed the example because it worked out better. It just didn't look as good in the earlier ones that we have here. Unfortunately, we're up against it. We made the change too late. Okay, I'm done.
Okay. All right, let's move on. I'm going to take us back to 36, which is special case 1.
Okay, special case 1. This is kind of an unusual case. It's where you have a non-concentric work point. Some engineers like to put their work point, let's say, at the corner of the gusset. Some fabricators like that too, because sometimes, especially if you have a connection to a column web, and you put the work point at the corner of the gusset, you generally come up with a smaller gusset. I personally don't like that, but if you want to do it, the special case 1 gives you a way to do it that's as consistent as possible with the work that Ralph Richard did. What I'm showing here is that the work point is at some arbitrary point here that you see, given by the coordinates x prime and y prime from the corner of the gusset. And this little formula down here, E equals E sub B minus y prime times sine theta minus E sub C minus x prime quantity times cosine theta. That E is this little eccentricity that you see here. The way that I would handle this is I would say, okay, I've got the center line of the brace, but the gravity line of the brace has been picked at some other point, that doesn't pass. I've got it wrong here. The center line of the brace, the engineer has specified that he wants this point, but the gravity axis of the brace goes through the center of gravity, the gravity axes of the column and the beam, and E is the eccentricity that's between those two. This slide gives you a way to calculate that. The next slide gives you the forces that will exist because of this. I have this P here should have been in tension. There should be an arrowhead on that P. The couple that exists on this gusset is P times E. And that couple then is distributed through the beam and the column in some way. This eta here is the percentage. Eta is the percentage of the moment that's in the beam. And if that's in the beam, then the remainder, 1 minus eta times m over 2, is in the column at the top and the bottom. If you do this, no matter what, you're always going to have couples in your beam and column, the extra moments in the beam and the column. So therefore, for this type of a situation, we can come up with a statically admissible internal force distribution for the connection by taking the forces that you see here, the H primes and the V primes, and adding them algebraically to the uniform force method forces that you would have gotten by assuming that the brace acts through this point. I'm saying the gravity line of action for the uniform force method. You come up with a completely admissible internal force field. However, you've got these couples in your beam and column. Therefore, the design of the beam and the column need to consider those couples if you want to satisfy, in a quote that I used in the first session, the niceties of structural mechanics. You could check it and see whether it really makes any difference or not. Sometimes it does, sometimes it doesn't. What's eta? Eta, well, these are the formulas to calculate the H prime and the V prime. They've basically gotten from just statics from these pictures that you see here. And eta, if you have an elastic analysis, it would be the I over L of the beam divided by the sum of the I over L's of the beam and the column. That would be an elastic analysis, or maybe you want to do it some sort of a plastic analysis. Look at the plastic moment of the beam and then the sum of the plastic moments. I don't know the right way to do this. If you're using an elastic analysis for your main frame design, I would say this is the right way to do it, the I over L stuff. If you're doing an inelastic analysis of this particular problem, then maybe something like this one is more appropriate. Special case 2. Special case 2, we alluded to that in the example that we saw. Sometimes we get too much shear in the beam. This R is a specified beam shear. And if R is taken as some percentage of UDL, what's UDL? The uniform design load. It's the design load that fully stresses this beam at the center under a uniform load. And a lot of people use this as a crutch rather than giving the connection design of the actual beam gravity shear. They might specify 1/2 UDL or 3/4 UDL or UDL at each end, say a composite situation. That really gets the stress, the shear stress in this beam web pretty darn close to what it can take. And now if you add to it the V sub B that you see in here, you can go over the top. So one way to handle that is to introduce a delta V sub B to basically reduce the amount of the brace vertical component V sub B that you see here that goes to the beam by an amount delta V sub B. This kind of shows it a little clearer. I've got, if the brace is in tension, the V sub B is going to be pulling up on the beam. I'm going to put a delta V sub B pushing back down. The R, if it's pushing down here, it's got to be pushing back up in the gusset to column connection. If V sub B is pulling up here, it's going to be pulling back down here. If delta V sub B is pushing down there, it's going to be pulling back up here. Now, you might say, wait a minute, R and V sub B are in opposite directions, so therefore I shouldn't be adding them. But I could reverse the brace force. It might be compression. If it's compression, then V sub B and R will be in the same direction. So it's my way to do this is to say, unless I've got a specific case where I absolutely know that the brace is always in tension and these two are always in opposite directions, I am going to assume the worst and hope for the best that R and V sub B add. If the gusset were down here on the bottom flange of this beam, say in the fourth quadrant, and the brace was in tension, then they would add. So it's, even though they're shown this way, and they're shown this way intentionally just to show the way they really act, you can't be sure that they're always going to be acting in those directions. This just shows you what happens if you do this. If we add a delta V sub B here, which we're reducing the vertical component between the gusset and the beam, we got to increase the vertical component between the gusset and the column. So you have a delta V sub B over here that adds to V sub C. So V sub C gets bigger. And what happens now, we got a delta V sub B here and a delta V sub B there. These are causing a counterclockwise couple on the gusset, and it needs to be reacted by a clockwise couple, which is V sub B times if the alpha and the alpha bar are the same, that term goes away. It's delta V sub B times alpha bar, the distance between the two delta V sub B's. One here at the centroid of the gusset to beam connection, and another one here at the centroid of the gusset to column connection. If alpha and alpha bar are not the same, then we have this extra term that you see here, V sub B times the quantity alpha minus alpha prime. All of these equations are given in part 13 of the manual, the 13th or the 14th, or even all the way back to, I believe, the second edition, and definitely the third edition, LRFD. So this just shows you what happens with the beam. The third one of the three free body diagrams we've got a delta V sub B that's pulling down here, and we've got another one that's pushing back up here. So these basically cancel each other out and have no effect whatsoever on the column. They do affect the gusset, though, and they affect the beam. What causes the use of this? Well, I really told you what causes it. If you insist on using some percentage of the strength of the beam, some percentage of UDL, the uniform design load, you are going to be basing your shear reactions on a beam strength rather than on floor loads. Most beams, especially those part of the lateral bracing system, are designed for stiffness, not strength. Check out your designs. Usually you're going to be designing these beams for at least a deflection limit, and you may have an axial force in it because of the bracing situation. These beams are going to be heavier than they need to just carry the gravity loads on the floor. This results in beams many times stronger than those required for strength, and larger shear reactions than those required for floor loads. Check one out. Check one of your designs. The engineers that are listening to this, if you use UDL or 3/4 UDL or whatever, calculate the load that you actually are using in pounds per square foot on the tributary area that contributes to that beam, and I'll bet you'd be surprised. You're probably talking about 1,000, 2,000 pounds per square foot, when the real load is probably more like 200. If the real loads were used, if the real gravity loads were used based on the loads rather than the beam strength, we probably would never, ever have to use special case 2. And I don't really like special case 2, but sometimes we have to do it to avoid double plates, which are expensive. Special case 3, this is spelled out in manual part 13. Basically, it's what you would do if you got a very shallow brace or a very steep brace. This shows a shallow brace with a large angle theta from the vertical. Why connect to the beam and the column? Just connect to the beam in this case. And if you had a very steep brace, connect to the column. That's really all special case 3 is. This, as I say, these are all the formulas. You can look this up in the manual part 13. This blows up what you see before. In the previous one, you could use a flat bar in here, which means it's very little fabrication on that, depending on if you can make it work. I mean, if you got a big nose over here, it might turn out that you're not passing too close to the centroid of this thing. Ideally, we should have alpha bar equal to alpha, but because of the geometry, you won't always do that. Note that one of the problems with this connection is MBC here. There's always going to be a moment between your beam and your column if you do this. That means that this connection down here is going to be hurt quite a bit by a couple. There's nothing you can do about it because I need to bring the V, the vertical component, over to the center of the column, and that's really what this couple is doing. It's transforming the vertical component of the brace over to the center of the column. Now, special case 4, which the next set of slides will cover this. This is something new. The name was actually coined just a few days ago by one of the people that's helping AISC produce the slides for this presentation. Basically what it does is it takes a connection to a column web but makes it look like it's to a column flange by taking an E sub C equal to the distance out, say, to the first column of bolts is the usual. I mean, I could take it out to the second, or if I had a double column of bolts here, I could go to the center of those. The idea is that the uniform force method doesn't know, the mathematics doesn't know that this is a column web or a column flange, so we could kind of fake it out. We can just use E sub C, and that gives us E sub C equal to the distance out to the first column of bolts rather than 0. And it's turned out in a lot of jobs that gives us a much more economical connection. This slide just shows you all the forces that you're going to generate. You would generate all these forces that you see here just using the usual uniform force method with an E sub B and an E sub C. And you might take beta equal to the distance down to the centroid of the gusset to column connection. And if you do that, and that's what we usually do, you're going to calculate an alpha, and it almost always turns out to be bigger than alpha bar. So therefore, you're going to have a couple on this horizontal edge here. I mean, we could move this brace out. We could make the gusset longer, but why bother? Why do all that? It's just more economical generally to allow a couple to exist on these interfaces sometimes. Now, these slides you've seen last time. They weren't called Special Case 4 because I wasn't calling it Special Case 4 a week ago. But you saw these slides, and I just want to go through this in a little more detail than we did before. The engineer of record for this particular job told us after the job was complete, and I said this last week, that the job finished out, completed, at $2 million below what they estimated the job would cost. They used the KISS method. They used the double clips. We used the uniform force method, and we used the Special Case 4, among other things. We used conventional and extended tabs. They replaced the more traditional double clips at jumbo columns, reducing both fabrication and erection costs. Imagine drilling all those holes in columns that have 4-inch flanges. I think I mentioned that last week, too. So I'm not going to dwell on this too much. But the uniform force method was used in novel ways. Basically, what we did is we used this Special Case 4, and we used X bolts. A lot of people think that X bolts, well, if you're going to use X bolts, you need additional inspection. But really, if the thickness of the ply adjacent to the nut satisfies certain requirements, as we'll see on the next slide, you may not need any inspection, any extra inspection. For instance, if we had 1-inch diameter bolts, if we have flush nut, which is the minimum, and we don't have any washer, we would have to have a ply next to the nut of about 5/8 of an inch, about 7/8 of an inch. Well, more than 3/4. I don't know what that is. It's probably 13/16 or something like that. But if I use a 5/8 washer, 5/32 washer, I can go down to about 5/8. And if I have a 1/4-inch stick through, I can go all the way down to about 3/8. So anything thicker than that, I'm not going to have threads in a shear plane. So you can really use X bolts in a lot of cases, and we use them all over the place. If we have a connection to a column web, like you see here, or a thin web or a thin plate, we use N-type because we don't want the extra inspection. So on this particular job, this is the Special Case 4 connection that actually was pulled off that PowerPoint job you saw. We had a 16 by 26 beam, 3/4-inch diameter, A325 bolts, and this is the actual design. And these are the force distributions. We saw that before. This is using E sub C equals 10 1/4 inches. The conventional way to do this would be to use E sub C equals 0, and if you do that, you'll get this design. And the next slide I'm going to dwell on a little bit more. We compared these two last week, the 1/2-inch tab and the 1-inch tab, and we compared the bolts, the welds, 5/16 to 5/8, and we compared the bolts to 3/4 over here and 1 inch, but I think actually that's a mistake. Those probably should be 7/8 bolts. But anyway, I don't want to dwell on that anymore. These are the forces. And if you actually calculate the forces on this, another homework problem for you. If you take the geometry that you saw on these and you go through the whole rigmarole, you should get the forces that you see on this slide. And this is what we used to design the one that you saw with the E sub C equals 10 1/4. So I want to go through this table a little bit more. We kind of sloughed over it last time, but look at the holes. We got 24 in the standard as opposed to 14. We have plate thicknesses of 1 inch as opposed to a 1/2 inch. The area of the holes here, that's for 7/8 diameter bolts as opposed to 3/4-inch bolts. We had 14.4 inches cubed area as opposed to 3. We've got 21% of the volume. That means that we don't have to drill, and we're drilling only 21% of what we would have had to do. The next one is instructive. For the standard case, we had 5/8 fillets. For the optimum, we had 5/16. The length, though, of the standard was 30 inches as opposed to 52.3. Yet when we come over here, we see 180 inches. How come? How come we had 30 and now we got 180? Whereas for the 5/16, we've got 15.3 and we still got, 53 52.3, and we still have 52.3. Well, the reason is that a 5/8 fillet weld is a 6-pass fillet weld. So if you take 30 times 6, you have the equivalent of 180 inches of single-pass weld as opposed to a 5/16 at 52.3. That's a single-pass weld. You only have 52.3 inches of weld. There's a heck of a difference in the savings there. And for the rest of it here, this is the area of the tabs and the volume of this material in feet cubed, and so you've got a weight reduction. The optimum is only 71% of the weight of the standard. So just looking at these numbers here, we saved 80% savings in drilling time, and we saved even more than that on the jumbo columns, because we use these tabs on jumbos as well as the light one that you see here. We had about a 50% savings in the welding consumables. I think it's actually more than that, but that was a reasonable estimate. And a 60% savings in labor. If you look at that 29, maybe we're talking about 70% instead of 60%. And coming over here to the weight, it only weighs about 71% of what you would have had in the standard way of doing this. All right. You've seen 4 different cases here. You actually have seen 5. You've seen the general uniform force method, which is not one of the special cases. There's no special case 1, 2, or 3, or 4 involved in that. So there's really 5 different cases that we've looked at. So we've looked at how to use it. We are going to, in the subsequent seminars, we'll look at design of a whole bunch of connections with this, or at least 2 in great detail anyway. The uniform force method, though, is not based on theory alone. It comes from work that was done by Ralph Richard. That was analytical, and it's also based on physical testing. This work by Ralph was analytical. He basically was using a nonlinear finite element program to solve problems that look like this. You can go back to the paper that I referenced on a previous slide, but what he did was he ran about 6 different cases. We started out looking at this with, say, welded on the horizontal edge and bolted on the vertical edge. Then we looked at bolted on this edge and welded on that edge. And then we looked at welded on both sides and bolted on both sides, and we didn't see a heck of a lot of difference. That's 4 cases right there. Then we looked at 2 more cases, and we looked at what's called a drag-through situation, where you got a force that goes through the column to the other side, and we looked at a case with top and bottom gussets. Now, these pictures here show only the bottom gusset, but there's about 6 different cases built into these teardrop-shaped regions that you see here. That was 60 degrees. That was the 30 degrees. This is a 60 degree, 45. These angles on this particular case are measured from the horizontal. The next is the 60 degrees measured from the horizontal, opposite from the way the uniform force method measures them. It doesn't really matter, but you can see that all of these resultants tend to intersect each other on the opposite side of the work point from the gusset. Some of them really look pretty good, some of them not so good, but if you go back, looking at the 45, I mean, they all looked pretty good at that one. Go back to this one, they all look pretty good. That gave me the idea, really, that maybe I can come up with some analytical way of representing this. And just looking at a 45-degree case, so what if we extended? What if we put arrows through these teardrop-shaped regions that you see that go more or less to the center of the gusset, and you see they intersect each other on the opposite side of the gusset from the work point. That was the genesis of this idea, that I tried to come up with a kind of a non-fuzzy way to represent this. So I say the force distribution shown on the previous 4 slides, based on the work of Ralph Richard, gave rise to the idea of a concentric, a coincident or a concurrent set of forces on the gusset, which you see here. You can see exactly in an analytical fashion exactly what Ralph was showing in all of these pictures that he had here, or most of them anyway. I agree they're not all exactly as nice as that, but it's still pretty darn good, pretty close to what he came up with. In addition to this analytical work, I wrote a paper in 1991 that was published in the conference proceedings of the AISC National Steel Construction Conference in 1991. A version of this is available on the Survey's website. And this is my T.R. Higgins paper from 1995. We compared 6 more or less full-scale connections, 3 of them by Radar Bjerholder and a graduate student at the time, Chakrabarti. These were done at the University of Alberta. These were tension only. This would really not be a really good connection for compression, but these were tension only. And there's 4 different A, B, C, and D, 4 different connections that are listed here. This is gusset to brace to gusset, gusset to beam, gusset to column, and beam to column. So keep those 4 letters in mind. These were 3 tests that were done by John Gross and his assistant Geraldine Cheok at NIST about 1989. Looking at these slides, this just lists all the limit states, and I am not going to go through these in any great detail, but there was an even dozen. You can see bolt fracture, you can see Whitmore buckling, Whitmore yield, bearing, tear out. Even back in those days, we distinguished between tear out and bearing, even though the spec still does not. And then looking at the 4 connections, A, B, C, and D, these are the limit states that apply to them. You can look at this at your leisure. You've got all this information, and then here are the physical test results. The first 3 were the Bjerholder's tests, and you can see just looking at test capacity versus predicted capacity, hell, we're right on the money. 1.01, this number should be just a little bit bigger than 1. 1.01, 1.04, 1.11, and even the failure interface was A, the predicted, and the test was A. An A, and this one wasn't the same interface, but we had one of the same limit states, 5. When we got to the second 3, these include frame action, which is not explicitly or even implicitly included in the uniform force method, and so they turn out to be conservative. I've always felt that if we could figure out a way to consider frame action in these connections, we could do a lot better than we're doing in the design of these connections. And there was a paper that myself and Pat Fortney, my colleague at Surveys, presented in Toronto there was a first step maybe in trying to come up with an analytical way of doing this. I wouldn't say it was 100% successful, but you can take a look at that paper. It's probably available from AISC. It's called The Effect of Frame Action on Vertical Bracing Connections. Okay, I think we're getting close to time, and Brent asked me to maybe skip this. If you have a non-orthogonal situation, we can generalize the uniform force method as seen in these slides. These formulas, all that you see here is the formulas are presented all the way back in 1999 in a book that was edited by a guy named Akbar Tamboli. There's a reference to the 2nd edition of that book in the references to this presentation. And you can find all these equations derived or given there. I don't actually derive them. I show you what they are. It's up to you to derive them. To derive them, you would have to go through the rigmarole that I did with the 3 equations, equation 1, 2, and 3, and show that you can make all of the forces intersect at a single point. This formula right here is the constraint in the non-orthogonal case. There's an example that's worked out in detail in the forthcoming design guide. I will not go through that here in detail because I think we're running out of time. But all of the slides for this are shown here. You can calculate all the forces. You can check it out for yourself. I want to make the point that you should not, in a non-orthogonal case, assume that it's orthogonal. Maybe if you have an angle of like a half a degree or something, yeah. In this case, the angle's about 9.5 degrees, and it makes a difference. You need to look at the non-orthogonal case when you have non-orthogonal situations, and that's all spelled out in the book. I'm just going through the calculations here pretty fast because I want to get to the last set of slides, which is on control points. A jack truss to a main truss. Now you might say, wait a minute, this is not a bracing connection. It is. I showed you the next slide last week. This is really a bracing connection. This is a job that was done in Boston. 25 stories of a 35 stories of a 38-story building sit on these trusses. This is the main truss. There's a jack truss that frames in here. You see the gusset for that. The next slide shows you the connection between a main truss and a jack truss, not the one exactly that we were looking at in the previous slide. And I wanted to point out that what we're doing here is we are slotting this near side gusset and passing the jack truss gusset through it to the inside of the far side main truss gusset. And the reason we're doing that is to get the vertical component of this jack truss brace, which was probably on the order of 2,000 kips, right dead center on the truss, main truss vertical. This job was done about 15 years ago. The one that you just saw. This one, I don't know when this one was done. This one has got a problem. You're probably going to point it out to me that I've got a welded connection to the column here and a bolted here. This is the way the engineer wanted it. This is the way we did it. I don't know. I mean, it's standing. I think it's probably all right because there's some relief here in this particular connection, the gusset to the beam connection. This is the main truss, and this is the jack truss. And I just really want to point out that what we're doing here is exactly what you saw on the previous one. I got to get the vertical component of this brace, which is 599 kips. I got to get it right dead center to this main truss vertical. And the way I do that is just a routine use of the uniform force method. This just shows the picture a little bit bigger so you can see it better. The next slide shows the breakdown of the forces. You can calculate all the forces here using the uniform force method. You can calculate the E sub B and the E sub C and the alpha and the beta. In this particular one, I took alpha. What did I take? I took beta equal to beta bar down here because I have no couple on this edge. And in this, because of the geometry, the alpha and the alpha bar were not the same, so therefore I have a couple of 1,030 kip inches on the gusset to column connection. I don't know why we did it this way. Actually, I didn't do this connection, but it's one that I know that was done at one of our divisions, and this is the way they did it because I reviewed the calculations and we talked to the engineer about what he wanted, and this is what he wanted. So coming back to the control points, the way that this really works, and I think it's pretty neat with the uniform force method, is that control point A is right here. Control point A is at the center line of the jack truss beam, top chord, and it's lined up with the truss core, the flange of the truss vertical. That point, I know exactly where that point is, because I know the half depth of this member. And control point B is right here, and it's at the bottom flange of the beam at the center of the column. Now, this is not drawn to scale. The distance between the bottom flange of the beam, this beam here, the jack truss top chord, and the bottom flange of the main truss cord, it's about 7/8 of an inch from here to here. This is not drawn to scale. You can see that better. I really should correct that, but you can see it better in one of the initial slides. You can see that darn thing is pretty darn close in there. The bottom flange of this 36 by 135 is about 7/8 of an inch above the bottom flange of this one, which is a 36 by, I think it's a 231. So there's really hardly any eccentricity in this connection because that's where control point B is. So you can solve problems like this, I think, pretty simple. It's pretty simple to do it. You can argue about whether you want to have bolted welded and welded bolted and all that, but that doesn't matter as far as the force distribution is concerned. It matters relative to how it's going to behave. And so kind of finishing up on this, I just bring back one of my earlier slides showing the uniform force method, the control point A, which we just talked about, and the control point B. These are the 2 points that you see right here in this particular slide. That's the beam control point. That's the column control point. And even though this is not shown very well here, this bottom flange is just a little bit above the faying surface here that's got 312 kips vertical and 125 kips shear, and there's a little couple on this, which would be 125 times, I think it's about 7/8 of an inch from where that work point is to the faying surface. So there you go. That kind of completes this. That's the uniform force method. I think what I've tried to show you here, its versatility. I've showed you its derivation. We said this last time, that connections can account for 50% of the cost of erected structural steel. I think with some of the connections that you see in this seminar, that's easily the case. I mean, the very first example was a very simple one. I would say that's probably maybe a 15 or 20% situation. Rational design of connections requires engineering knowledge, and that's really the gist of all of this. There is no software out here to do this stuff. You may use software, very sophisticated software, to do your mainframe analysis and design, but there is nothing available to do what you see in this connection right here. Not that I know of anyway. You would have to write your own software. You would have to do it yourself. Even we do these connections day in and day out. We don't have any software to do that. It's such a special connection that we just have to sit down, start from scratch, calculate E sub E, E sub C, alpha, beta, and all the forces, guarantee that we satisfy equilibrium, and move on. So rational design of connections requires engineering knowledge. The reason that I'm interested in this subject is that exactly. I cannot use computer programs to do this. I have to understand what I'm doing. So the uniform force method is a rational method. The KISS method is fine, too, if you want to use it. So is the parallel force method. But I don't think they give you as good a design as the uniform force method does. As good in the sense that it satisfies equilibrium, and it's very economic, and it's probably closest to the true internal solution. In the context of the corollary to the lower bound theorem, it provides a design closer to the actual unknown admissible internal force distribution than any other known method, and you saw that last time. And it provides pretty economical connections when properly used. And the geometry and loads determine whether to use the general UFM, which was really the first example that we did, or special cases 1, 2, and 3, which we have not done any cases for those yet. Well, special case 4, which was the one that we did with the jack truss. And I think that brings me to the end of this. This reference 1 here is the one that's got the non-orthogonal uniform force method developed in it. That's the second edition. The first edition is about 1999. It's got the same stuff in it. That particular book applies it to a aircraft hangar top chord with a sloping top chord, and gives you a pretty neat design, I think, compared to what was originally done using a version of the KISS method. Anyway, there's a couple of references here that have some chapters that I have as either author or co-author that you can look at and see. Maybe you can get some more information on this stuff if you're interested. And I guess that brings us to the end, and we're right about on time, Brent. So I hand it back to you.
Okay, thank you, Bill. We do have a handful of questions here. The first question I have for you is, how do you account for the beam reaction due to gravity loads on the beam in addition to the vertical component of the brace force?
In the usual situation, we assume that the gravity force applies to, say a column. If we're talking about a column flange connection, we apply it at the face of the flange, and we don't try to get it to the center of the column. The logic there would be, if you didn't have a bracing connection, you would apply that force at the flange and not concern yourself about it. Another part of that is that programs like Ram Steel actually assume an eccentricity there anyway in the design of the column. But we do not explicitly bring that shear to the center of the column as we do the vertical component of the brace. If you were going to a column web, it's there anyway. But if you use this E sub C not equal to 0, equal to 10 1/4 here, you need to bring the shear from 10 1/4 inches out, the beam shear, to the face of the column. And that's included, if you go through the calculations that I showed you here for that particular example. I'm backing up. I don't remember what the number is, but it's back a few. If you look at the forces that we had in that particular connection, you remember what the number is, Brent, that you can just go to it? instead of me backing.
I'm looking for it. Which are you talking about? The first example?
No, it's the special case 4 example.
Okay, hold on, Bill. Stop.
I'm almost there anyway, but maybe you'll get there before me.
Bill, I'll get there.
Want me to stop?
Yep.
Okay. If you look at this distribution where I give you the numbers, where do I give you the numbers? Come on. Yeah, no, that's not it. I think it's the next one. Yeah, this one. That couple that you see, the 275 kip inches on the bolts, is based on two things. It's based on the 46.6 times 1.5 inches, which gets me from where I'm assuming E sub C is, and it's also the 20 kips times the distance out to the centroid of that bolt group, which is 10.25 plus another 1.5 inches. I think it's 11.75. That 275 kip inches gets my 20 kips shear all the way back to the column. And you see on the column I got 40. The 46.6 actually includes that. If you look at this three-body diagram, you see 26.6 here, but you see 46.6 here because that's including the 20. And that 46.6 is carried into the bolt group, and it's carried through all the way to the face of the column web. So what we're doing generally, if we go to a column web, we get the shear to the column web because the strength of the column, the flexural strength of the column, about the weak axis is generally like a third or so of what it is about the major axis. But it's always been AISC's policy that beam shears to column flanges include no eccentricity. You just put the shear at the face of the column flange. That's not satisfying the niceties of structural mechanics, but that's the way it's been done, I think, from time immemorial. But if you want to do that, then you would have to modify the uniform force method to do it. And it can be done. I mean, it's been done right here for a web connection, which really was treated like a flange connection. I can do it to any connection I want, if that's what you want to do. It's going to give you extra forces to deal with. I did not consider that in any of these connections where I'm going to a column flange. We did not consider it in the first example that we did, and we didn't consider it in the jack truss example. Okay, next.
Okay, I'm going to take us back to special case, well, I guess case 1. It's not special case. Actually, I'm sorry. Yeah, special case 1.
Slide 36, right.
Okay, so the question is this. Should special case 1 be avoided if doing a delegated connection design and not having input on the framing member sizes? In other words, if I'm not the EOR and didn't size the framing members, would I be introducing moments into the framing that was not accounted for in the original EOR design?
I'd say the answer to that is, I think, yes. I would not use this unless the engineer of record told me that he wants his work point at some oddball place. And we've had jobs where they put it right here at the center of the column at the top flange of the beam. We've had others where they put it at the corner of the gusset. If that's what you want, I will do the calculations the way that you see here, and then I will tell you that you've got couples in your beam and your column. If I assume an elastic analysis that this is what they are, I calculate the eta factor that way, and you tell me whether it's okay or not. But no, I can't use this unless I'm I actually designed the main frame. But if the engineer tells me that's what he wants, I might assume that he's taking care of it. But I think I would show the couples just to make sure that he knows what he's getting himself into here. Last week I said that when people were using the KISS method in years past, and I know this because I've talked to people from American Bridge and Bethlehem Fabrication, they didn't do any of this fancy stuff. But you can't get away with that today. If you don't do it, somebody's going to call you on it. And I think you need to have an admissible internal force field. You need to satisfy the niceties of structural mechanics, except for a few cases where AISC has traditionally not done it. For instance, the 3-inch eccentricity in a shop bolted double clip connection generally is not, the eccentricity is not considered. Why? Because it's been done that way for years, and there's never been a problem with it. If it were welded, you would. What's the difference? The difference is that welding is newer than bolting, which comes from rivets. I think I said some of this last week. If you really want to dot the I's and cross the T's, you need to consider every eccentricity. But some of them have not been considered for many years, and there's been no problem. Anyway, next.
Okay. The next question is in regards to special case 3. Let me get there 1 second. Okay, the question is this regarding special case 3. The AISC examples that are found online using special case 3 refer to the moment M sub BC as negligible. As the connection engineer, is it okay to ignore such a moment when designing a bracing connection?
Well, I don't think it's negligible. I don't know. I mean, if the vertical component is pretty small, and you have a small column, but really, I mean, you got a small connection. Maybe if you got a small column and a deep beam, so you can get lots of bolts in there, maybe it is. Maybe it would be negligible, but I would not say that it's negligible. And I said that in my presentation, that one of the problems with this is that you got that couple. I would not ignore it. I would not ignore that couple. On the other hand, I am ignoring a couple, if you like, because I'm delivering R to the flange, and I'm not worried about half the beam depth in that, half the column depth in that case. But that's only because it's been done that way for years. Not that it's right, but I mean it seems to work okay. And also, as I said, programs like RAM Steel actually do include an eccentricity in your column design for beam shear connections to column flanges. There's a discussion of this in the manual. There has been, I think, since the 2nd edition, LRFD, about why it probably doesn't matter. Because if anyway, I don't want to get into that, but I think it's in Part 9 or Part 10 where we talk about connection rigidity and whether or not you really need to consider the fact that you may have a rigid moment here or a simple connection here. Anyway, take a look at that. Maybe it'll shed some light on the R part of it. But as far as what the questioner is asking, I don't think you should ignore or say that M sub BC is negligible. I believe Part 13 says you need to consider it. I don't know what the design examples do. Okay. Obviously, I didn't do that one, so I can pull my punch as pilot. I don't know.
Okay, I'm going back to the jack truss example. I'm on slide 109.
Got it.
The question is, what is the basis for the control points A and B on this slide? How did you determine these control points?
The control point A is at the gravity axis of the beam, which is the jack truss top chord in this case, and it's at the position of where if you imagine extending the column flange where my green arrow is, extend it up until I reach the center of the beam, that's the point. That's the definition of control point A. So I know exactly where that point is. I know the size of this column down here, which is the truss vertical. I know the distance from the center to the flange. So I know the distance exactly to that point from a reference point of the center of the column. And I know exactly its distance from the bottom flange of the beam because it's right at the gravity axis of the beam. I had another slide following this. I mean, it's this point right here. It's that point. It's at the half depth of the beam at the face of the column flange. It's this point right here where my green arrow is. You know exactly where that is. And point B is at the center of the column, at the top flange of the beam in this case. And if I go back to this, point B is at the bottom flange of the beam, which is right here, and at the center of the column. And I pointed out that the distance between the bottom flange of this beam and the bottom flange of that beam is less than an inch. It's about 7/8 of an inch. This is not shown right here. This flange here should be right about in the center of the flange of the main truss top chord. Okay, next.
Okay, I'm going to jump back to special case 2. All right, here's the overall picture for special case 2.
Yep.
How does special case 2 impact the forces at the control points?
How does special case 2 impact the forces at the control points? Well, control point A is this point right here. That's the A was at the beam to column, right? I can't remember which is A and B, but I think that's A. That's one of the two control points. And how does it affect it? I've got R, and I've got V sub B, and I've got delta V sub B. So I've got R, I'd say plus V sub B minus delta V sub B as the shear, and I've got H sub C as the axial, or the horizontal, or the normal force on that connection. And this point, the other point, the other control point is really not shown in this picture, is it? It's not that point. It's this one right here. Where is that? That point isn't really shown in here, but it's right here. It's right here. It doesn't have any effect on this point. It doesn't have any effect on that point. I don't know why I keep getting an arrow stuck there. Do you know, Brent? But that is the column control point. It's right here, right there, and that point is at the center line of the column at the top flange of the beam. The top flange of the beam is at E sub B. At the center line of the column, it's right there. That isn't an interface in this connection unless I have a splice or something there. Like I did in the jack truss, I actually had a connection at this location. In this particular case, that control point is somewhat irrelevant. I'm not calculating any forces there except for one thing. I need this H sub C, and this is what a lot of people miss. H sub C is applied from the gusset to the column, but it also has to be applied between the beam and the column. So you see an H sub C over here on the column pulling, and you see an H sub C over here pushing. That means that the column needs to be good for a shear equal to H sub C. So there really is a shear on this control point, the column control point at this point, but it's in the column. It's not a connection. But I usually check that. I mean, if H sub C is a number that's bigger than the shear strength of this column, I need to put a double plate in here. There's some discussion of this kind of thing on similar connections in the second edition of the seismic manual. Okay, next.
Okay, I'm going to slide back to I think I want to be here, slide 14. I think this will be the right one, but for the actually, let's go here. I'm not sure it's going to work either. Shoot. Okay, so for the calculation of R, here's the question. For the calculation of R, does beta or alpha have to equal their bar equivalent? Can R just be calculated with beta and alpha?
Alpha and beta must satisfy this constraint. Any alpha and beta that satisfy that constraint can be used in this formula R. So if I have alpha and beta, if I have alpha equals alpha bar, which is the ideal case, and beta equals beta bar, then I've got alpha and beta that satisfy this constraint. A lot of times, and you saw in the example problem, the first one, that we took beta equal to beta bar, which I think was 8.5, and alpha turned out to be what was it? 11.5, but alpha bar was 10.5. I have to use the 11.5 in this formula. So I'm not sure I understand the question, but whatever alpha and beta you use, they need to satisfy this constraint, which is the formula in the box. I can choose a beta and calculate an alpha and substitute that in here. I can choose an alpha and calculate a beta and substitute that in here. I could have an alpha and a beta that satisfy the constraint because I know what they are. I picked them to satisfy in advance. I can substitute those in here. But whatever I pick, alpha and beta must satisfy this equation in the box.
Okay. Thank you very much, Bill. We are now out of time, and I want to get through a couple more announcements before we finish up here. So thank you again, Bill.